A major subject in mechanics is rotational kinetics and energy, how things spin, how they rotate. And this ends up being important for a lot of engineering, obviously, and for fundamental understandings of how the world works. All right. As expected, angular position is measured by the angle some location makes with reference to some standard axis. In other words, a position of an angle, or the position in angles. By convention, we usually denote the angle by theta, much like we denote linear positions as x, and we measure theta positive from the plus x axis. Usually, as before we have conventions, usually we would say positive is counterclockwise, going from the x-axis to the y-axis. This gives us a so-called right-handed coordinate system and is convenient. It's not impossible to do the other way any more than the fact that we could have plus x going to the left. We could have plus theta going clockwise. But if you don't specify, the convention is to start at the x-axis and then go counterclockwise for positive or increasing theta. All right, so we have, if you imagine we had like a dot of paint on a wheel as it spun around, when it was here, we'd say it's at theta equals 0, and then theta would be the angle that it sweeps out. You can measure your angle in any unit that you'd like, such as degrees or revolutions, 1 rev being once around a circle. But nature has a preferred unit for angles called the radian, and preferred is in quotes, and actually units, we'll see, should be in quotes. But there is a way in which the mathematics is most simple, even though this is often counterintuitive to students who like degrees, but you only like degrees because you're used to degrees. If you think about it, like, why are there 360 degrees in a circle? And there's no good mathematical reason for that. It's just that somebody thousands of years ago defined it that way because the ancient Sumerians had a base 60 system, and because going around the sun once, or for the sun going around the earth once in a geocentric system, there were 360 days. Of course, there's really 365 days, but that's incredibly awkward. 360, on the other hand, is very divisible. It's divisible by 1 and 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, and then 24 and 36 and all the other divisors out there. So it's highly divisible, especially in the low range. So it becomes easy to work with if you don't have decimals for your fractions, if you can only deal with integer fractions. And that's honestly why it's 360 degrees. Everything else, why is a right angle 90 degrees? Because it's 1/4 of a circle, and the circle is 360 degrees. It's chosen for certain computational convenience, but there's nothing in the math that works. On the other hand, radians are built into the number line. They're built into the way that numbers are, and we'll see that. They make calculus the simplest possible, and any equations that have other units have to include conversion factors so as to compensate for that. The definition of the radian is straightforward, if non-obvious. 1 radian is the angle at which the arc length s is exactly equal to the radius of the circle. So remember, arc length is your distance along the circle, so these are all different arc lengths. And so if we sweep out an angle theta, and we take this arc length, this path, we want it to be that s is r theta. So theta is defined as s over r. Of course, if we go all the way around the circle once, then s is one circumference, which is 2 pi r. And so we have that if theta is defined as s over r, then theta around a circle is 2 pi r over r, or of course 2 pi. So there are 2 pi radians in one circle. So we have our conversion factor that 2 pi equals 360 degrees. You might have learned radians in your math classes, and they might have taught you the conversion factor was take the number of degrees and multiply by pi over 180. And that's fine and true, but I would argue conceptually less useful. What you're really doing is taking your angle in degrees and then multiplying by the conversion factor 2 pi over 360. You're really doing something where you're saying basically something like theta in radians is to theta in degrees as 2 pi radians is to 360 degrees. And of course, 2 pi over 360 is pi over 180. So of course it works out algebraically the same, but it's hard to remember. Whereas remember that a circle is 360 degrees, which you've known for a very, very long time. And then remember it's related to the circumference, so it's also 2 pi. Makes that conversion factor pretty easy to remember. And so that's honestly how I remember it, and I think it's useful for you to think about it that way. Of course, all of this ends up meaning that 1 radian is approximately 57.3 degrees, a little bit less than 60 because it's a little bit more than 1/6. If that seems pretty awkward to you, you're certainly not alone, but nature does prefer this. Also notice, and this is kind of bizarre, but this definition, right, if theta is S over R, well, S is measured in meters and R is measured in meters, so theta is measured in nothings. Theta is a non-dimensional unit. Angles are dimensionless. All right, we'll often write things like 2 radians, but that's sort of colloquial. We could really just say the angle is 2. If you don't attach a unit, that would have to be radians. It's kind of interesting. Physicists and engineers will almost obsessively put the radians in, whereas mathematicians have no problem saying like theta is 3 pi over 4 or something like that, and having the radians be implicit. And honestly, in this case, the mathematicians are probably more correct. We'll find out that the radian is not really a unit of measure. It's a counting unit. It's a counting term, like dozen. It doesn't actually add anything to what you're counting. Since objects can rotate, the angular position of a location on an object can change. Sort of duh. We define the angular displacement as delta theta, and using our usual definition, delta theta means later theta minus earlier theta, or theta final minus theta initial, or however you want to remember it. And thus we can define the average angular velocity and instantaneous angular velocities, denoted with the symbol omega. Please note that this is the symbol omega. It is not a W. It is not a curly W. It's an omega. And both write and pronounce it, please, as it is itself and not something different. So we define omega average as delta theta over delta t, and then omega is the limit as delta t becomes small, or d theta over dt. Notice that these would have the units of radians per second, which is really just per seconds, but we'll usually keep the radian there, keep track of it. Notice how these are designed to be exactly analogous to the kinematic definitions of one-dimensional motion, where, of course, we would have had stuff like v average is delta x over delta t, and so on. As an illustration, here's an object that has negative angular velocity, constant negative angular velocity, and we see that it's rotating in the negative direction. We'd often write that on a picture like this. All right, in general, the period of something is the time required for it to repeat once. In the case of rotations, this is the time to complete exactly one revolution. It's denoted by the symbol capital T and is measured in units of time, usually seconds. If the angular velocity is constant, then there is a simple relationship between the velocity and period. Omega is omega average, and therefore is delta theta over t. But in one circle, delta theta is 2 pi, and so we get that omega t equals 2 pi, or omega is 2 pi over t, or t is 2 pi over omega. Related concept is the frequency f, which is the number of repetitions per unit of time. Frequency is measured in cycles per second, or inverse seconds, which is more often written as hertz, and from the definition we see that the physical frequency f is 1 over the period, or f times t is 1. All right, by now it's probably no surprise that since the angular velocity of an object can vary in time, giving us delta omega is omega f minus omega I, then we'd also define angular acceleration, denoted by the letter alpha, and having units of radians per second squared. Notice that alpha is not an A, right? We're talking about alpha, not A. That's going to be really important to keep track of. That's the place where students often make silly but tragic errors, and try not to do that. And we define, as before, that the acceleration is the change of velocity per unit time, but now we use the angular versions, and that the actual instantaneous acceleration would be the limit again. All right. Here we see motion with a positive initial position, but negative initial velocity, and with a constant positive acceleration. So how do we know it has positive initial position? Because we start with theta equals 0, and increasing theta is counterclockwise. And you'll see when it starts going that it has negative omega because it's going originally this way. But because it has an acceleration, oops. All right, we'll do it again once it wraps around. It's going like this at the start, but there's an acceleration which is this way because it is going to counteract the initial negative velocity. See, and it stops it, and it goes back the other way. And since the acceleration is constant, but I let this run for too long, it ends up going way too quickly this way. But there you go. Okay, let's see how this goes. Sketch an angular acceleration versus time graph given the angular velocity versus time graph shown for this over the same time interval. So remember that we have that alpha is delta omega delta t, which means it's the slope on an omega t graph. So if we look here, we say that during the first two time intervals, it's got some positive but constant number. So maybe something like this. But then during this time interval, omega is constant, so its slope is 0. So this drops down and becomes, this, but it's only one time interval. And then we see here that we have a negative slope, but it's steeper than this, so it should be more negative. So let's drop down to like maybe there. And we have some value that's about right. And then finally it goes back to 0 because at the end of the motion, again, omega is 0.